Today's video is prompted by a couple of things. So firstly, it's in reply to a video that was made by PyroPete from the UKFR, who turned on his Generation 3 DB04r module 1,000 times to try and prove or disprove that it would fire or misfire, on turn on. I will try and link his video in down below so you can see that if you haven't already. And today I wanted to have a look at that a bit more scientifically to see whether it is possible to misfire, but also that the version that PyroPete used, the Generation 3 model, would not have been out when some of the reports about the misfirings happened. So I think they were probably more likely to be using the version 1, the Generation 1 model. So that is the model that I will be testing today. So in a previous teardown video I did of both modules, I discussed the danger that the firepower is turned on at the same time as the logic power, and this can cause some instability during power up. But worse than that, on the Generation 1, because of the bounce of the circuit switch, the power switch, the rocker switch, that could also be seen at the MOSFET gate, which means the MOSFET will try and conduct during those transients because of that bouncing of the switch. And this is I thought this was very poorly designed. And I proposed the idea that these transients could, if it gets severe enough, cause a misfire because obviously there's some element there of the MOSFET firing gate being interacted with during the switching process. The question is, though, that still remains is how long do these transients last and how much current do these transients deliver through the circuitry, and whether that could in reality fire igniter or not. It would have to be a considerable length of time to fire an igniter, which is generally not how a transient works. You're normally looking, at around 10 microseconds or less. So at any current, that would probably not fire an igniter. So this is a very sort of, what do you say? It's not necessarily a great hypothesis, because already we know that the switching time would be so short. It's very unlikely, unless it has an extremely high current, which wouldn't happen, then it's unlikely to be this. But we'll go through the process, we'll test it out and see what happens, see what we get. So first we need to do is look at the switch that they've used, and this is what's in front of us. This is I've opened the module up and found that with the same ID of the switch, this is what's come up, and it's a Chinese market switch. It looks pretty accurate to the version that I've got, and it doesn't have a huge amount of information on it. It claims here it can go up to 10,000 cycles of the switching life. It does not say if that's the mechanical life or the electrical life, because switches don't just have one life. You can have a mechanical life, which is the physical action of the components in the switch moving, and then you have the electrical side, which is the contacts and how long they last, because as the contacts draw together, there'll always be an amount when they get close but not quite touching, and that can cause arcing, which can damage the beds of the contacts. And then over time, particularly if you've got high current being drawn through the switching cycle, you'll find that erodes, or not say erodes, but it damages the switch, and the contacts become dirty, etc., and it doesn't switch very well. And then obviously the mechanical life would be like the physical action of the switch breaking down, and that, so it stops physically moving. The mechanical life does not affect the electrical characteristics of the switch. So they're two usually separated, but on here they've just said switch and life cycles, so we don't know quite what that is. I'm now going to also, later on in the video at the end, I'll show you another set of results which I've done using a better switch which I've bought from RS. This is the switch that I've bought. Let me just show you the top. It's the panel mount PR series rocker switches, and as you can see on this, it actually shows you the mechanics of the switch. So you can see on this one that the two contacts are actually in parallel with each other. So as the rocker switch moves, it just pushes on that bar that pushes the switch, the contacts, down against the contacts of the bottom contact. So because they're always in line with each other vertically, it's not like when people look at rocker switches, they think the actual contact is sort of moving, it's rolling across. It's not generally in most switches. You'll find it's just a vertical action, but the switch itself creates that rocker, And you can see that actually there's lots of little parts in this. So you'd have this tiny little spring, you have this big, usually like a rubber bung that moves across the contact, and there'll be a purchase point for the contact somewhere, etc. And if we have a look, it says mechanical life 50,000 operations, but the electrical life won't be anywhere near that, I shouldn't think. There it is. So if it's the 6 amps, it's about 10,000. I think that's right, isn't it? 6 amps. Does it say which one it is? UL. It's about 6,000, sorry. So between the 3 amps and 6 amps, depending on what the voltage you're driving it across, they reckon it's about between 10 to 10,000. And that's for the contact life. So that's the electrical life. So even though it claims that it has a mechanical life of over 50,000 operations or cycles, you can see you get much less on the electrical contacts. And that's pretty common in most switches. And it goes on and does all the various coding and that, and the various types of switches that they sell in the same format. So you can see this alone is much better technical document, and you can see the relevant legislation and regulations that it applies to and what it's been tested to. So how are we going to achieve this? Well, we're going to take a couple of measurements at the same time, and I set up a rig to do that. So we start from the top left. Over here we have a current sense amplifier on a circuit board. So this is the problem we've got, is I want to take current readings through the queue as the transients are switching to see what actually current gets drawn for the queue, and this requires a very fast way of detecting current. I've looked into all sorts of probes and that to try and achieve this, and the expense got quite horrific. So what I've designed is my own current sense amplifier board. So where you have a precision 4 terminal resistor, and you basically have a differential amplifier type arrangement in a chipset. It's already designed as a separate specialist application, and it takes a measurement either side of the resistor, and because you know the precision value of it and you know the voltage drop across it, you can then work out the current flowing through it. And that's what it's doing. If you notice, it actually is in line with, if you look from the cabling point of view, it comes into this queue here, and then there is another resistor here that comes out and then goes back round, and it goes out the photograph and then down back onto the board. And the reason for this is because I've actually looked at the shunt resistor which is on the board, which takes the readings, and then I've combined that with a fixed value resistor, which is the resistor sitting down there outside the board, and that will create the 2.8 ohms effective load, which it would be if there was an igniter connected. So we've actually loaded the queue with the correct resistance. Now if we go slightly lower, we can see we have 3 green cables down here coming out of the module. So I've created a load of jump leads from inside the module which have been soldered in and glued, and I'll show you a picture of that up screen now so you can see what I've done. And you can see that basically this allows us to probe certain points of the circuit without taking it from the bed of the test rig. So although this isn't a perfect solution, because obviously we've got flying leads now, and that's going to create some parasitic effects into the scope traces we're going to take, it's a necessary evil so that we can obviously create a system where we don't need to keep moving the DB04r off the test bed, and then that will create, every time we do this test, it will be slightly different. I want to try and make it the same throughout the whole test. So how are we going to switch it on and off? Well, over here we can see we have a servo, and this will move the power switch. The test rig has been designed so that we don't create a huge amount of pressure in the middle of the switch, because that's not really how a human presses a switch. We normally push the top or the bottom, and with a servo, if you imagine the servo arcs, then obviously you're going to have a problem. That center part of the arc is the center of the switch, and it pushes it harder there. So to get round that, I've made the rig slightly springy so that the DB04r will move slightly if the pressure there gets too much or too hard, so it becomes unnatural. But again, unfortunately, a servo switching a switch does not really replicate a human switching it very accurately, unfortunately. But it's just a better way of making a more consistent result, and a better way of sampling the scope traces without creating inconsistencies through my own way of switching. So down the bottom right here, we have our LCD, which is going to be showing us our amount of times we've switched. We will be doing this in bouts of 250 cycles. So we'll do 250 cycles of the switch, and then we'll take a scope trace, and then we'll do another 250, and then we'll do another scope trace. So we'll be doing over 11,000 switches in total, 11,000 cycles. Down here, where we can see the 6-volt power supply, this is for the servo. So the servo runs off a separate power supply because of the noise, compared to the PIC chip, which is here, which is doing our control of the servo and our control for the LCD. The power for the current sense amplifier is also ran from a separate supply, so that's very, very smooth, because we're trying to detect very, very small millivolts changes across a resistor, so we need to make sure that our power rail is absolutely clean, otherwise that's going to cause problems with our measurements. So that sort of tells you how we're going to be going through the switch cycle, and then I just want to have a quick look at the scope so you're going to be seeing to show you what's going to happen. So the yellow trace is the side of the switch of the board. So effectively, so you'll find that the battery's power goes through the switch and then onto the board. So I'm measuring onto the board. So what you're seeing is the actual switching from 0 to 5 volts on the top there. And this is the switch bounces. And in case you're wondering why it seems that we have here, we don't seem to be starting at 0 volts. This is because we've effectively, because we're cycling this, and this scope trace was taken during a cycle about 1 second between the switches, there is a bulk capacitance in the DB04r which probably hasn't drained fully yet back to 0 volts. So if you were to look at the previous part of this scope before we started to turn it back on again, you'd probably notice that there would be a very slow discharge curve that would come in and then across, sort of like that. And then that's sort of obviously where it got to before we start turning it back on again. So that explains why it's not quite 0 volts. Let's have a quick look at the scaling here, because that's also important. So 2 volts, so we've got 2 volts per division up here. So 246, you can see that would be the top trace. And then the second trace, which is the light blue, it's the cyan type trace. This is the gate of the MOSFET. So we're looking at the transients on the MOSFET gate, and that is 500 millivolts per division. So that is not the equivalent of the top trace, which is 2 volts per division. So just be aware that these aren't directly comparable in terms of the scaling. And then the bottom is our current trace going through the Q, and you can see obviously the current moving through the Q, and that's at 50 milliamps at the moment on this trace, but I do change that during the operation and during the testing to 20 milliamps. So just be wary of that. And the reason why I change is because I begin to realize that 50 milliamps actually is the transient is not going to produce a huge current, which I was worried about at the beginning. So I made it as 50 milliamps so I could capture the whole peak, but that's not going to happen. So I changed it to 20 milliamps so we get some more detail on the current trace rather than just the peaks. So that's the explanation of the traces. So next I'm going to show you a video of the actual switching. Then I'll show you a slideshow of the scope traces, and at the top left it will give you the number of cycles. And then I'll come back and I'll do some commentary on the results. I'll then change the switch over to the new one that I've got from RS, the better supposedly the better one, the more expensive one. See if that makes a difference to our turn on, and then summarize the results. So our results were pretty consistent throughout the whole test, which is rather surprising. I was expecting when we hit the 11,000 cycles that the switch would start to become more sort of spongy and you might get more bounces or it might not turn on properly in that. And there is a short video which I'll quickly show you now of the switch becoming slightly less reliable during the operation. And you can see during the video that as it tries to turn off, although the servo sweeps across, you can see that the switch sort of sticks and then goes off. So I'll show you that while I'm speaking. So in terms of the current draw, the worst trace is this one in front of us now, which is showing us about 100 milliamps spike. And that's over, what's that, space of 20 microseconds, 25 microseconds. So that's not significant enough to fire igniter. None of these spikes are significant enough to fire igniter. So it just seems that this doesn't seem like this concept has legs. And especially if we look at this, you may actually also ask why, if we look at the end of the trace here, what is this current draw here? That is, of course, the current going through the Q to light the LED for the continuity. If you remember the diagram, the circuit diagram which I'll show up here, we have two MOSFETs back to back, which has the same gate drive, and then we have to the left of that the LED, which will get brighter through the top connection because it shorts out, the igniter shorts out the parallel resistor, and that's what that current is there. That's the current going through the igniter to get the brighter LED, and then obviously the current spikes to some extent will be the transient in the MOSFETs. Now, the problem we have also is that the MOSFET datasheet doesn't tell us what happens in these moments. We're actually working offside the charts of the MOSFET datasheet. So, it's very unreliable knowing exactly if this is the realities of how the MOSFET's working. So, but the results I think are fairly sort of clear that I don't think we're ever going to get a misfire on turn on, even with the transients and that we're seeing, because the bouncing in that just does not produce a high enough spike for long enough in terms of the current to fire an igniter. What is interesting that when we change the switch over to the more expensive RS version, we get a slightly different trace. So this is our trace from that switch. You can see it's got no bouncing at all, which is just unbelievable. I've done this numerous times as well just to check this, and this is true. This is just one switch. There's no bouncing at all in it. It's completely clean. You do get the current spike obviously at the beginning like you do on the gate, but again this is only 40-60 milliamps, so not enough to worry about, and again over like 25 microseconds. So I think realistically we've proven that a switching of the switch on turn on is not going to cause a misfire in this way, not from the actual switch transients, the bounce of the switch. So unless there is a more complicated reason, such as a software glitch in the microcontroller which turns on, which sort of pulses the MOSFET to a longer degree, I don't think we're ever going to see this truly show us the results we need. Because if you look at the datasheet for the igniter, we're nowhere near the timings for surefire. So we don't need to be, for example, we can be lower than that for fire and igniter, but it just seems we're so much lower than that. We're in the microseconds that it seems very unlikely on these pulses we're ever going to get an igniter to fire. And I think, to be honest with you, PyroPete sort of proved that in his video. But there we go. So I think really we can take from this that the switch is very, 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 very unlikely to cause fire in a turn on. I can't see any evidence behind it yet in my tests. I hope you've enjoyed that video.